Okay, thank you. And thanks for the invite as well. So I'm going to be talking about equations in the Heisenberg group, formal languages, and quadratic equations in the ring of integers. It's a very long title. I know I almost feel like a mathematical biologist at this point. Okay, so don't worry if there's stuff in that title that isn't entirely clear to you. I will hopefully define everything as I go along. And I'll start with what an equation in a group means. Now, I'm not going to define this formally because the formal definition is actually not very informative. Equations in groups are basically what you would think they are. So you take a group G, you take a set V, well, I'll say it's always finite, of variables. And then an equation is just an expression in G and elements of V and V inverse. So formally, I suppose, an equation in G it's an element of the free product of G. With f of V. So what that really means is just an expression in elements of G, i.e. constants, and these variables. And when I say a finite set of variables, formally I just mean a finite set that we haven't used. So a solution, I mean, formally that's a special type of homomorphism from G free product f of V back to G, but I'm just going to think of it as, actually, I'm going to write this slightly better. So an element is that, and we write it omega equals 1. So there's the equals in the equation to make it a bit more clear. So a solution is a tuple, a size of V tuple of elements of G, and I'll call the solution, I don't know, X, such that substituting X into omega gives a word that equals the identity. Okay, so what do I really mean by that? I mean, it's kind of what you would think it would be if you've done equations in school at any point. You sort of substitute something such that you get equality. And because we're in a group, we can, if we have, you know, omega equals nu, we can just put nu on one side and make it equal to 1. So group equations are a little bit easier in that regard. Okay, so let's give a quick example of what this is. So let's pick a group. I don't know. Let's pick the free group on A and B, and we'll take our set of variables to be, let's just take it to be a single variable X. And then an equation could be, for example, X A, in fact, yeah, X A B. In fact, no, just X A, X inverse A inverse equals 1. That's the equation. And as I'm sure you all know, that commutation in free groups, because this is obviously just a commutator, is if and only if it's a sort of power of it. So the solutions to this equation are just a to the n for all powers of n. So that's an example. Okay, so I mean, as to why you might be interested in equations is they give you lots of sort of useful things, like they can tell you whether stuff commutes, they can tell you whether something is torsion. It's just stuff like that. And you'd be surprised how many random problems you can get in groups that can be reduced to sort of solving an equation, at least in some sense of the term. Okay, so unless anybody has any questions as to that, I think I will move on to the next bit. Okay, so the next bit is equations and languages. So just in case anyone's unsure, by a formal language, I mean a set of words over a given alphabet. So I'll quickly define that. So if you take sigma to be an alphabet, which is just a finite set, a word over sigma is a finite sequence of elements of sigma, and we don't write with brackets and commas, we just concatenate them. So denoted W1 up to, actually let's use A, I don't like W, A1 up to AN, rather than with brackets and commas. And then a language. Over sigma is just a set of words. And that's kind of it. That's what a language is. Okay, so how do you use equations to study languages? So one of the main ways equations are studied is you say, is there an algorithm where I take as input an equation in your given group and it will output whether or not there's a solution? So just yes or no. This can be really useful in some cases because it determines, say, it can determine many things, like whether a centralizer is non-empty of a given element, for example, or stuff like that. However, if you want to actually know more, like say some sensible enumeration of the solutions, one has to ask the question, well, what do you mean by a sensible enumeration? Like, how do you describe solutions? And recently there's been a lot of attempts to describe them using languages. So you take a nice class of languages and you write the solutions out as sort of languages in that class. So how do you write a solution as a language, given that you've said it's a tuple, and languages are usually sort of just one element things. You can think of a regular normal form, as we've heard in a couple of talks ago, that's a language, but it only represents one element at a time. So you have to do some tricks to deal with this. And there are multiple ways you can do it, but the way I'm going to show you is for various reasons that I'm not going to say, but is my opinion the best way of doing it. So the way you do it is we'll take curly E to be a system of equations. And by a system, I just mean a finite set of equations. And a solution to the system is just any solution to all of the equations in the system. The solution language I forgot to do in G. So G is going to be a group. Sigma is going to be a finite generating set, so we need to assume it's finite generated. And I'm going to take eta to be a normal form for G. So it's going to take an element of G and assign it. We're thinking of it as a function. So it's going to take an element of G and assign us a word that represents G. So for example, if G was the identity, it could assign us the empty word. Or just AA inverse. It's just, I'm not putting any conditions on this. It can be any normal form. So the solution language 2E, with respect to sigma and eta, in practice, sigma doesn't really matter. You can change sigma, but changing eta is much more difficult. Is the language, well, I'll take G1 up to Gn to be a solution to curly E. And then we'll just take the normal form word of G1. We'll concatenate that with a hash. Then we'll do the normal form word of G2. And we'll concatenate that with a hash. And so on to the normal form word of Gn. And I did not leave enough room to do that. So apologies if you can't read it. That's supposed to say Gn and then eta. So the idea is we've just sort of removed the brackets and replaced the commas with hashes, and then replaced each of these things with the normal form word representative of them. Yeah, so that is a language, but you may notice this new symbol. So this is new. So the idea is we've picked some symbol hash that's not in sigma or sigma inverse. So It's just disjoint. So this is actually a language over the alphabet, sigma union, sigma inverse union hash. Okay, so now we have a language, but sort of what do we want to do with this language? I mentioned we say it's a nice sort of class of language, and I'm now going to spend a little bit of time explaining what class of language I want it to be. I'm not going to go into too many details for this because it's a bit annoying, but well, they're really nice classes of languages, but the definition is very technical. So they're going to be called EDTOL languages. And I'm going to define them with an example. There is a formal definition that will come out of this, but I'll use an example to do it. And the language I'm going to show is EDTOL is going to be A to the n hash A to the n, where n is in the naturals. And I'll say the natural, actually, let's not have that debate. It's in the integers greater than or equal to 0. You may notice that this is the solution to the equation x equals y. Admittedly, it's in the semi-group of the naturals the integers greater than or equal to 0 rather than the group. But to avoid having to deal with the inverses with an automaton, I'm just going to do the positive case. Okay, so how do we do this with an EDTOL system? For a start, an EDTOL system has an alphabet, the sort of terminal alphabet. This is just the alphabet of the languages. So in this case, our alphabet is just A and hash. We don't need any inverses because, again, this is actually just a semi-group. You also need an extended alphabet. So this is going to be everything in sigma and some extra symbols you work with. And I'm only going to need one extra symbol. I'm going to call it perp. You can think of this, if you've seen context-free grammars, as sort of the union of the terminals and the non-terminals. You then need a start word, which I'll normally called omega. This can be thought of as the equivalent of the start symbol in a context-free language. And in my case, the start word is going to be omega hash omega. And this is anything, any word over C, or C star just is the set of all words over C. And then you need the rational control. And this is where it gets a little bit more complicated. This is a rational set of endomorphisms of C star. So yeah, it sounds quite nasty. But it's where C star is actually now the free monoid, because if you endow this set with concatenation, you get the free monoid. Now this sounds rather horrible, but it isn't actually, because you can, an endomorphism, like with homomorphisms between free groups, an endomorphism from a free monoid is defined once you know its action on the generating set. So all I need to tell you is where everything in C goes. So let's define this rational set using a finite state automaton, and we'll sort of see how it goes. And hopefully it will become clear. So I'm going to need my start state, which is going to be Q0. And I'm going to have an accept state, which I'll call Q1. I'm going to have an edge from here to here, from Q0 to Q0, labeled with the endomorphism defined by mapping perp to perp A and fixing everything else. And then I'm going to have another edge going from Q0 to Q1 that maps perp to the empty word. And that is all I'm going to do. So what's actually going on here? So I could just go, I start off with perp hash perp. Now I could just follow this edge and I get hash, which is A to the naught hash A to the naught, which is good. I could go do this edge once. So then I get perp hash perp, which would go to perp A hash perp A. And then I could say follow this edge at this point, and that would then go to A hash A, which is still in our language. In fact, I could do this n times, and then I would get perp hash perp goes to perp A to the n hash perp A to the n, which then would go to, if we followed this edge after doing this edge n times, A to the n hash A to the n. So it's clear that the language that I said was the language accepted by this, wherever I said that, this language here, I'll call it L. It's contained in the language that this machine accepts. Oh, I should have said what you're actually supposed to do. So the language that is accepted by it is just the words that you take by taking omega and applying one of these endomorphisms, such that you end up with something that is indeed in your terminal alphabet sigma. So the language accepted by this ED2L system, and I'll call it H, is just, I'm going to use right actions, so forgive me if you don't like that. It's omega H, where H is in R. That is not a good R. Intersection words over sigma. So it's clear from what I've just written that the language L is contained in the language of this ED2L system. And spoiler alert, an ED2L language is one that's accepted by an ED2L system, if you hadn't guessed that already. But also the other way around is true, because if I were to do any sort of path in this automaton, is just a bunch of these and then that. So it's just n of these and then that. And that always gives us a to the n hash, a to the n. Okay, so that is it for ED2L languages. So are there any questions, or shall I move on? Okay, in that case, let's talk about ED2L languages and equations. So in 2016, Ciobanu, Diekert and Elder proved that this, the solution language to a system of equations in a free group is ED2L. And this is with respect to the normal form of reduced words, you know, the standard normal form of a free group. And this kind of gave a nice alternative way of depicting solutions to equations in free groups. It is true, though, that in free groups there was a way of looking at solutions, because Razborov gave a method for sort of understanding the whole set of solutions rather than just whether one exists or not. But this is an alternative way of doing it. And unlike Razborov's method, this is actually very generalizable. So stuff followed after that. So I'm not going to give these in the right order, because some of them were published more than once, just to make our sort of lives difficult. But Diekert and Elder extended this to virtually free groups. So they showed that with respect to a sensible normal form, equations in virtually free groups, or systems of equations, are ED2L. Diekert, Yesh, and Kofleitner did the same for right-angled Artin groups. Ciobanu and Elder did it for hyperbolic groups. And they actually showed that for hyperbolic groups, you can pick any quasi-geodesic normal form and it will work. So any remotely sensible normal form is good for hyperbolic groups. So Alex Avets and myself did it for virtually abelian groups. And then slightly more recently, I showed that it was true for groups that are virtually direct products of hyperbolic groups. So I've now got 10 minutes left, and you may have noticed that I've not mentioned the Heisenberg group once in this entire talk, despite it being the start of my title. So maybe I'll just give a quick thing to that. So it's well known, and I think Romankov was the first to show this, that systems of equations in nilpotent groups are undecidable, as in there's no algorithm that can determine if a given system of equations admits a solution. And this is true if you restrict to free nilpotent groups, which includes the Heisenberg group. And it's still true if you get rid of the word systems and you just look at single equations. However, Duchin, Liang, and Shapiro did show recently, well, in 2014, so not that recently, I suppose now. And Shapiro, not Liang. They showed that single equations in the Heisenberg group are decidable. So although they're undecidable in general for free nilpotent groups, for the Heisenberg group, it is an exceptional case and it does work. They in fact showed it's true for class 2 nilpotent groups with a virtually cyclic commutator subgroup. But the key point is in the Heisenberg group. And I'll use H of Z to denote the Heisenberg group. Okay, so single equations are decidable. So given everything in my talk, are the languages EDTOL? Well, it's actually true that an equation in the Heisenberg group, and I don't think I'll have time to go through all the details of why this is true, but an equation in the Heisenberg group, a single one, is equivalent to a quadratic equation. And by that, I mean modulo a little bit of mess, but it is equivalent. Well, it's not modulo mess, but it's modulo actually converting it in the right way, because you end up with more variables in the integers. Is equivalent to a quadratic equation in the ring of integers. So again, we're talking about ring equations now, but I'm not going to define an equation in the integers because I'm sure all of you have seen an equation in the integers before and have a general idea of what it means to be an equation in the integers. And in fact, you can actually say a bit more about this. So if I say in n variables here, then this becomes in 2n variables. And these solution sets are basically equal, subject to just moving stuff around a bit. They are basically equal. So these statements are the same. The trouble is that these are actually quite hard. They are decidable. That is how Duch and Yang and Shapiro showed this. They showed it's equivalent to these equations, and then they applied a result of Siegel that shows that they're decidable. Aside from the fact that the result doesn't seem to be available in English, it's also quite difficult even after you start translating it. So it's not an easy way of doing it. And it's also, as far as I've understood, not that constructive. My guess as to whether they are ED2L in general is no. And so I thought, well, can I show that the solutions to single variable equations are not ED2L? Because those are equivalent to 2 variable equations. And 2 variable quadratic equations are solvable quite nicely. There's a much nicer algorithm which involves reducing them to the generalized Pell's equation, which is x squared minus dy squared equals n. And you can then reduce this to x squared minus dy squared equals 1, the Pell's equation. And the solutions to Pell's equations are very much ED2L. As are these. Unfortunately, the conversion from this to the general thing requires a bit more mess, which I'm not going to go into now. But my hope was showing that if you could show that these plus the mess was not ED2L, it would show that equations in the Heisenberg group are not ED2L. That was not what I showed. After working through and understanding what these look like, I ended up showing that 2 variable quadratic equations in the ring of integers are ED2L. And I was quite surprised by that because certainly at the beginning, I was very much intending to do this to get a much stronger theorem showing that equations in general in the are not ED2L. But that was not the case. And of course, this gives the single variable corollary in the Heisenberg group are ED2L. Or solutions to, I suppose I should say, but I think you know what I mean by that. And I think I'll stop there, given that is exactly 9:55. So, yeah, thank you.
Thank you. Let's thank the speaker. Are there any questions?
Are there techniques to
What?
sorry? Are there techniques to show that a language is not EDTOL, or
Sorry, could you say that again?
are there techniques, strategies to prove that a language is not EDTOL, or?
Not really. That's part of the issue. I was trying to develop some for this, but when I ended up showing it was EDTOL, they didn't get finished. So you can. It's been shown that. I mean, there is a pumping lemma, but the pumping lemma can pretty much. The only languages I've really seen it used to show are not EDTOL is stuff of the form W in a 2-letter or more alphabet, with the length of W equals something like n squared for any n, or 2 to the n, or some, bigger than function that's strictly bigger than linear. So those are not EDTOL, but you can't really show much for sort of the sorts of languages you get that are in a normal form. It's also known that the set of words over a free group alphabet of rank 2 or more that equal the identity in the free group. And this doesn't work in Z. That's not known. It's whether if you were to just take words over A and A inverse that equal the identity in Z, whether that would be EDTOL, although the conjecture is not. So these are the sort of quintessential examples of non-EDTOL languages. The techniques used to prove this could be replicated for other things, but it doesn't seem that they can go much out of this idea of language. You might be able to do it for something slightly more complicated, but still it's going to be that sort of thing. And this one, there haven't really been any techniques done out of it. It's a very long paper that they used to show that this is not EDTOL. And yeah, it's not very nice. So in answer, not really.
Sure, thanks.
So since we have about 2 minutes left, I'd just like to ask one thing. Could you just scroll up to the part where you mentioned the Romenikov result about systems of equations in nilpotent groups are undecidable?
Yes.
Here. So originally you mentioned that systems of equations in pre-nilpotent groups are undecidable. Then you crossed out systems of equations, and then underneath that you say single equations are decidable in Heisenberg group. Am I misreading, or is there?
I mean, in general. So if I give you a nilpotent group, there's not necessarily going to exist. There are nilpotent groups where this doesn't work. So I suppose I should have been a bit more careful with that. It's true that if you're given a nilpotent group, then it's true that if you were just given an arbitrary nilpotent group, there's going to be no algorithm. But if you were to give it a special one that's quite nice, like it's abelian, for example, that will be. So I was a bit cheeky there. I was talking about it as a class at once rather than a single group. Maybe I should be more precise in some. There we go. Is that?
Yeah,
is that better?
Like rereading the exact statement on the slide. It should have been obvious to me, but yeah, thank you. So are there any other questions? Okay, if there are no other questions, let's just thank Alex once more.